Hello, everybody. Welcome back. Today we're going to do section 6.4, which is called the definite integral. This is an immediate follow-up to section 6.2, where we talk about the indefinite integral. So in section 6.1 and 6.2, we talked about how to integrate functions. Some little f dx, you integrate that, and the result is some function we called big F, which is the integral of the little function f that you're integrating. Now, when you integrate, we always have a plus c on the end of these types of indefinite integrals. So the result of an indefinite integral from section 6.1 and 6.2 was that you had a function as a result plus a constant. The result of integrating an indefinite integral is a function. For a definite integral, the thing that we're going to do today is just a tad different. What you'll see is you'll have to integrate some function little f from a to b, and the result is going to be a number instead of the function, big F. So instead of getting a result that's a function, big F, the result you get of this is a number. This is the difference between an indefinite and a definite integral. A definite integral, you get a number punched out at the end. An indefinite integral, the result is a function. So this is actually a stepping stone. You first do an indefinite integration, and then to do a definite integral, you're just plugging in numbers, essentially, into your integral function, big F. So let's kind of talk about this a little bit. If you have a function little f that we're trying to find the integral of, and little f is continuous on an interval a to b, so there's a region of the x-axis where your function is continuous, then we call the definite integral, the thing that we're doing today, from a to b, is this symbol I just drew up above. It's this little integration symbol with an a and b on it. Now, the number a is called the lower bound. It's the first number you see in this interval, a to b. So the first number you see is called the lower bound, and the second value you see in your interval is called the upper bound. And symbolically, we always put that on our little integration symbol up top. So we have the integral of little f that we're going to find to be evaluated from lower bound a to upper bound b. So you put whatever those numbers are, top and bottom of your integral sign. So as I mentioned, the number a is called the lower bound, a is the lower bound, and b is called the upper bound. Put it on top of the little integration sign. So what does this mean? In practice, what it means is you're going to integrate things just like you learned how to do in 6.1 and 6.2. You'll integrate your little f to get your original function, big F, and then we put this little sign here, means to be evaluated from the lower bound to the upper bound. Basically, what that means is you're going to plug in the upper bound b into your function and plug in the lower bound a into your function and subtract them. So to find a definite integral means you integrate as normal, but at the end, you're going to plug in two values into your big F function and subtract them. So it's like one or two additional steps. You integrate, and then instead of putting a plus c on the end, you plug in numbers and subtract them. You'll be plugging in the number b into your big F, you'll be plugging in a number a into your big F, and you subtract them. It's always f of b minus f of a, f of the upper bound minus f of the lower bound. So our result will be a number because I'm basically plugging numbers in to my function big F after I get it. Now, definite integrals behave just like indefinite integrals, where you can take the antiderivative of each part of a added function. You can take the integral of a first function plus or minus the integral of a second function. So let's practice evaluating definite integrals. Now, as I mentioned before, evaluating definite integrals starts out exactly like how you do indefinite integrals. You just integrate. So if we have the function fx squared, we acknowledge that, okay, that 2 right there is a power, so I'm going to do the integral power rule. So the integral power rule says that when you have x squared, you want to increase the power by 1 and divide by the increased power. So the first thing I'm going to do, maybe to help get rid of some confusion, whenever you have a constant like 5 multiplied in front of your function, you can actually remove it out of the integral sign and put it out front. So I'm going to have 5 times the integral from minus 5 to 3 of x squared dx. Now I mentioned this, we knew this is a power rule, so let's do our antiderivative power rule. Current power is 2, so you increase the power by 1, x to the 2 plus 1 is 3, and you divide by that increased power, x cubed over 3. But then I have this 5 that I've got to make sure to copy down, so it becomes 5 times x cubed over 3. Now this is the part from section 6.1 where I'd put a plus c on the end and call it done. But since this is a definite integral, I'm going to end up plugging in numbers into this thing instead. So we put a little vertical sign here. That means to be evaluated from the lower bound, minus 5, to the upper bound, minus 3. I haven't done anything with those fellas yet, but this little vertical sign is like a reminder of, okay, I'm going to do it. I have to do it here in a minute. Now, we might fix this up a little bit. This is the same as 5 times 1/3 times x cubed. So you might write that as 5/3 x cubed. So I have 5/3 x cubed to be evaluated from minus 5 to minus 3. So here's where we deviate from what we learned before. So now, instead of putting a plus c and calling it done, now is where, in order to do the next step, you plug in the upper bound, the number that's sitting on the top, minus 3. Plug in minus 3 into this function, big F here, and then plug in the lower bound, with the number that's sitting on the bottom, and then you subtract. Subtract upper bound minus lower bound. And then we will evaluate, have a number as a result. So the first thing I'm going to do, I'm going to take minus 3 and plug it into 5/3 x cubed. Now the calculator is definitely going to be our friend today. So I have 5/3 times, plug negative 3 into that, negative 3 cubed. So this is me plugging in the upper number. And now I have to subtract, and this is part of the formula, subtract what you get when you plug in the lower number. So now plug minus 5 into that. You have 5/3 times negative 5 cubed. Plug minus 5/3, minus 5 into x cubed. So now I have two different values that I'm going to subtract. I plugged in the upper number, and I subtract what I get when I plug in the lower number. It's called the lower bound. And so we punch this out in our calculator to get a result. Now you can do this in as many steps as you like to feel comfortable with it. Let me decrease the brightness so you can see my screen here. All right, so we have 5/3 times negative 3 cubed, and that gives me negative 45 from that term. And you subtract what we get here. So let's punch out this part. We have 5/3 times negative 5 cubed, which is negative 208.33333. Now this, it is a good idea to try to keep no rounding error. So a lot of times what I'll do is try to write this as a fraction so that I don't have any error. So if I go to the math key here and press that top thing called frac, that will write negative 2.08.33 as a fraction. And that's what it looks like. Negative 625 divided by 3 is negative 208.33. It's a way of making it look a little nicer. There we go. So now I have negative 45 minus negative 625 over 3. Punch that out. it becomes minus 45 plus 625 over 3. And we will have our answer. Negative 45 plus 625 divided by 3 is 163.333333. But I think we could probably write that as a fraction again, math frac. That's actually equal to 490 divided by 3. In each of these numbers, either one of these numbers is correct. It does say that it says find the exact answer. So this one would be the exact answer, meaning there's no rounding error. Or if you do punch it out as a decimal, make sure to round to 2 decimal places. So if that were the case, the answer would be 1.163.33. And that is the answer to A. So you do your usual integral, but instead of putting a plus C on the end and calling it done, you're going to plug in 2 numbers, upper number first, plug in the lower number last, and then you subtract them, and the result you get is a value. Now this value has some meaning. We're done with this question, by the way. That is the answer in the box there. But just as a sidetrack, what does that mean? What is that number? Well, as it happens, if we go back to our front page here, as it happens, the number you get by evaluating this, upper bound minus lower bound, is actually the area under the curve between your function and the x-axis. So if you can imagine, I have my function, doing whatever. Let's say it looks like this. And I have an interval A to B region that I'm looking at. The integral that we just found, the number that you find by doing this, is actually the area between the curve and the x-axis and those values of x. The area. That's what that number means. So the number we just got is actually the area under this curve, or between this curve and the x-axis between -5 and -3. It didn't ask that, but that's a good, interesting thing to know. So let's do this again. Practice makes perfect. I have the integral from 5 to 16 of 8 over x dx. Now, if I want to, before I get started, you might think of this as 8 times 1 over x dx. Also, we would call 5 is called the lower bound. It's sitting down there on the bottom. And 16 here is called the upper bound. And it's sitting along the top. But what that means is they're considering integrate this function on the interval 5 to 16. That's really what we're doing here. Integrating between 5 and 16. So lower number, upper number. Anyway, let's get back to work. 5 to 16. Let's take this 8 and relocate it outside the integral. That's the same as 8 times the integral from 5 to 16 of 1 over x dx. So then I can look, what is the integral of 1 over x dx? That's the same as x to the -1. And as it happened, we can recall from section 6.1 that the integral of 1 over x, or that is, i.e. x to the -1, is ln of x. So I can go ahead and integrate this. This is ln of x times 8 when I integrate. But this is where, in section 6.1, I would have done a plus c and been done. But since we're doing definite integrals, and I have these numbers here, that means they want me to evaluate this, and we use a little vertical line, it means to be evaluated, from 5 to 16. What that means is you're going to plug in 16, plug in 5, and subtract them. Make sure that you plug in the upper number first. So you have 8 ln of 16, plug in for x, minus, so we have the upper number first, minus what you get when you plug in the lower number, 8 ln of 5. And you get out your calculator and you punch this out. You will have your answer. We have 8 ln of 16 minus 8 ln of 5. We get is 9.305 and some change, but it does say to round to 2 decimal places in our direction, so that would be 9.31. Now that is my answer to the definite integral. It's 9.31. But if I want to assign this some meaning, that is the area in units between this curve and the x-axis between 5 and 16. All right, let's keep on moving. Now this one says, find the integral from 2 to 5 of 6 plus 7e to the x dx. So you first have to integrate, use your integration rules that you learned from section 6.1, and then when you integrate, you'll be plugging in numbers. Now 2, reminder, is called the lower bound. 5 is called the upper bound. So what this means is you are integrating on the interval 2 to 5. Lower number, upper number. So this is a FYI, that's what that means. Let's take the integral of 6 and 7e to the x. Remember, as long as you have multiple terms right here and the power on the outside of the parentheses is 1, meaning there's not really a power there at all, you can take the antiderivative of each term separately. What is the antiderivative of 6? What is the antiderivative of 7e to the x? Let's go ahead and do that. The antiderivative of 6 is 6x, and the antiderivative of e is itself. So you end up with 7e to the x. The constant 7 just kind of carries on for the ride, and the antiderivative of e to the x is e to the x. Now, instead of doing a plus c and calling it done, this is where I go, okay, this is to be evaluated from 2 to 5, which means I haven't started plugging in numbers yet, but I will right now. First, upper number. We do upper number first, and then plug that in, and then plug in what you get. We plug in the lower number and subtract them. All right, so let's plug in the 5, and you want to plug 5 into this whole thing here. 6 times 5 plus 7e to the 5. There you go. That's our upper number. Now plug in your lower number. You got to subtract it. Subtract what you get when you plug in your lower number. 6 times 2 plus 7e to the 2. Now this is where you can punch this in your calculator. We can also leave it exact by not punching it in our calculator. So let me do this all the way down as far as I can. First, 6 times 5 is 30. So this becomes 30 plus 7e to the 5. Now this is going to be a nasty looking decimal, but I'm going to leave it as this for now. Minus 6 times 2 is 12 plus 7e squared. I'll leave 7e squared as a not decimal. So let's distribute the minus sign here. You end up with minus 12 minus 7e squared. There we go. 30 minus 12 is 18. So in its exact form, we have 30 minus 18 plus 7e to the 5th minus 7e squared. Exact meanings, I haven't punched this out and made it a nasty looking decimal. So you could maybe enter it like this into your homework, but if we want to punch this out and find its decimal value and round, let's see what we get here. So I need 18 plus 7e to the 5th minus 7e squared. And that's what I have. We round to 2 decimal places, it said. So this is 1005.17. And this is the result of our definite integral. So you can think of definite integrals as being like one step further than where you would normally stop in section 6.1 and 6.2. We do our integration rules, but instead of doing a plus c and calling it done, we actually plug in numbers. Plug in top number, plug in bottom number, and subtract them. So my result isn't a function, it's a number. Let's do part D here. We have integral from 1 to b of -3 over square root of x dx, where b is a constant. So they're saying, well, let's treat this as a number. We're going to pretend it's a number, but it's going to be some random number. We don't know exactly what it is, but we still have to treat it as a number. That is, treat it as a constant. So that means that I'm going to do exactly the same thing I normally would. And don't pay attention to that b at all until you get to the point where you're supposed to start plugging it in. So let's first think about how I would integrate this. Remember, even though I have numbers, top and bottom, lower bound and upper bound, you still have to do an integration rule on all of this first. So it is helpful to manipulate the function little f inside your integral into something that you can identify and integrate. Now the square root of x is x to the 1/2. And you might recall from section 6.1 that if you have x in the bottom of a simple fraction like this, it's actually very beneficial and proper to take the x and pop it up into the numerator by making the power negative. Now, I have not integrated yet. No integration rules have happened. That's why I keep writing my little integration sign. All I'm doing is manipulating this guy into looking a little more friendly for doing the integrating. I haven't actually started doing it yet. So now that it's -3x to the -1/2, this is where I go, okay, I see a -1/2 power here. So I'm going to have to do the integration power rule on this in order to integrate. So let's do the power rule. Remember, the power rule is 1 over r plus 1, x to the r plus 1, or if you like writing it with the value here in the bottom, it's x to the r plus 1 over r plus 1. Both of those are equivalent, this one or that one. This version is just where you multiply those two things together. Let's stick with using this one for that, for my formula this time. My r is -1/2. So if I'm going to follow my power rule, first, maybe we should ignore the -3. The -3 comes down. This is -3 times whatever my power rule is. Now let's do a power rule. X to the -1/2. R is -1/2. So you have 1 over -1/2 plus 1, which is +1/2. X to the -1/2 plus 1. We should simplify this down, but here's the power rule in action. And this is where I go, this is to be evaluated from 1 to b. Let's not start plugging numbers into anything yet until I make this look a little nicer. So let's see. I have 1 over -1/2 plus 1. -1/2 plus 1 is 1/2. So that becomes -3 times 1 over 1/2. X to the -1/2 plus 1 is 1/2. Now this flips. This is 1 divided by 1/2. 1 divided by 1/2. If you multiply by the reciprocal, this is the same as 1 times 2 over 1, which is 2. So this whole bit right here becomes the value 2. It's algebraically equivalent. We have 2x to the 1/2 in here. And this is all still to be evaluated from 1 to b. Now this becomes -3 times 2, -6x to the 1/2. So now this looks a little nicer. And this is my integral This is my function, big F. But instead of putting a plus C on it and calling it done, this is where now I'm going to start plugging in numbers. So the first thing you do, remember, is plug in the upper number and subtract what you get when you plug in the lower number. So we're going to take the upper number, B, and plug it in for X. Let's pretend like it's a number and nothing's wrong. Plug in the upper number, B, and we go, okay, minus 6B to the 1/2. Since we don't know what B is, we just have to leave it like that. You plug B in for X, and there you go. Upper bound minus lower bound. Plug in the lower number into this whole thing. -6, 1 to the 1/2. Now, since this is a number, you can evaluate it. 1 to the 1/2 is square root of 1, and square root of 1 is 1. So you have -6b to the 1/2 minus -6 times 1, which is -6. Minus minus becomes plus, so this becomes -6b to the 1/2 plus 6. And then we're done. Since I don't have a value of b, and b is just arbitrary, some random constant that we don't know what it is, I can't punch this out any further. If I don't know what b is, I don't know what -6b to the 1/2 plus 6 is. So this would have to be my answer, and you'd have to enter it like this. And this is fine. I tried to plug in numbers, and this is as close as I got. We're done.